Okay, now we'll see about the relationship between moment and radius of curvature. Now you consider an elemental area delta A at a distance y from the neutral axis in the beam. This is a beam, and let this be an arbitrary cross section of this beam. You consider a small elemental area delta A at a distance y from the neutral axis. Now this is subjected to bending. This beam is subjected to bending. As a result of this, there will be development of stress on the cross section of the beam. Let F be the stress on the element. We can write F equal to, we have already derived F equal to E by R into Y. Therefore, force on this element is equal to, what is the force on this element? Force is equal to stress into area, F into delta A, which is equal to E by R into Y into delta A. Now, due to the application of the moment, the resistive stress is developed on the area, and this will lead to the force. And this we can write the moment of this force on this elemental area about the neutral axis as this force into distance y. Okay, so this is the moment of this resisting force about the neutral axis. So what is the moment of this resisting force about the neutral axis? Moment of this resisting force about neutral axis equal to E by R into Y into delta A into Y. This is the moment multiplying with distance. We can write E by R into Y square into delta A. So the total moment of resistance of the cross section is will be equal to the sum of the moments due to the elemental areas. Let us represent this as m dash sigma of E by R into Y square into delta A. So E and R are constants. We can take it outside. E by R into sigma of Y square into delta A. Now what is moment of inertia? Moment of inertia is, we can also define it as second moment of area. So we can see here delta A is multiplied twice with Y. So this is the second moment of area. So we can write I is equal to sigma of Y square into delta A. This is the moment of inertia. Moment of inertia is second moment of area. So we can write I is equal to sigma of Y square into delta A, which is the centroidal moment of inertia. Now we have got the equation m dash is equal to E by R into, instead of sigma of Y square into delta A, we can write I. Now for equilibrium, this moment of resistance should be equal to the applied moment, that is m dash moment of resistance should be equal to the applied moment m. So we can write here m is equal to E by R into I, or m by I equal to E by R. Now we have already derived E by R equal to F by Y. So we can write this is equal to F by Y. So this is known as the bending equation. M by I equal to F by Y equal to E by R is known as the bending equation, where M is the bending moment, I is the moment of inertia about centroidal axis, F is the bending stress, Y is the distance of the fiber from the neutral axis, E is the Young's modulus, and R is the radius of curvature. Okay. So this is the relationship between bending moment, moment of inertia, Young's modulus, radius of curvature, bending stress, and distance of neutral axis, distance of any section from the neutral axis, distance of the fiber from the neutral axis. Now we'll see how to find out the moment carrying capacity of a section. Now from the bending equation we have the equation m by I equal to F by Y, or you can write bending stress F equal to m by I into Y. This shows that the bending stress is maximum at the extreme fiber because F increases with the increase in Y for a particular cross section and particular moment, applied moment. So it shows that this bending stress is maximum on the extreme fiber where Y is maximum. In any design, this extreme fiber stress should not exceed the permissible stress. So if F permissible is the permissible stress, that is F permissible is the permissible stress, the maximum stress should always be less than the permissible stress. So F max should always be less than or equal to F permissible. So the bending stress is maximum on the extreme fiber where Y is maximum, and in any design this extreme fiber stress should not exceed the maximum permissible stress. So if F per is the permissible stress, then in any design F maximum should be less than or equal to F permissible. So we can write m by I into Y max, because maximum stress will be at the extreme fiber, should be less than F permissible. If M is taken as the maximum moment carrying capacity of the section, M by I into Y max is equal to the permissible stress. If M is taken as the maximum moment carrying capacity of the section, then we can write maximum moment carrying capacity of the section we can write m by I into Y max is equal to F permissible, or the maximum moment carrying capacity M can be written as M equal to I by Y max into F permissible. The moment of inertia I and extreme fiber distance Y max are the properties of the cross section. Hence I by Y max is a property of a cross section, and it is termed as section modulus. So I by Y max is known as section modulus, and it is denoted by the letter Z. That is the moment of inertia and the extreme fiber stress, fiber distance Y max are the properties of the cross section. Hence I by Y max is the property of cross sectional area and is termed as section modulus, and this is denoted by the letter Z. Thus moment carrying capacity of a section is given by M equal to F permissible into Z. Moment carrying capacity of a section is given as moment carrying capacity of a section M is equal to F permissible into Z. Okay. So if the permissible stresses in tension and compression are different, moment carrying capacity in tension and compression are found separately by considering the respective extreme fibers, and the smallest one is taken as the moment carrying capacity of the section. So you have to find out what is the moment carrying capacity for both the compression fiber and tension fiber, and you have to take the smallest moment carrying capacity as the actual moment carrying capacity of the cross section. Okay. So in all these you have to write the units. You know moment of inertia has the unit millimeter raised to 4 and Y has the unit millimeter. So the unit of Z will be equal to I by Y. This is millimeter raised to 4 by millimeter. So unit of Z equal to millimeter cube. So we can find out the expression for various sections. Like a rectangular section, the section modulus will be equal to, what is the section modulus for a rectangular section? Of breadth b and depth d. You know Ix, because the bending happens about the x-axis. We have to take the bending moment about the x-axis, which is equal to b d cube by 12, and z will be equal to I by y, Ix divided by y max. Now what is y max? Y max is the distance of neutral axis from the extreme fiber. Both the fibers will be at the same distance from the neutral axis. Because the neutral axis coincides with the centroidal axis, you can write this as d by 2. So the equation becomes bd cube by 12 divided by d by 2. So this is equal to bd square by 6. So this is the value of z. Now in the case of a hollow rectangular section with symmetrically placed opening, now if you have a hollow rectangular section like this, we can find out the section modulus like, if b and d are the external dimensions and small b and small d are the internal dimensions, we can write Ix is equal to b d cube by 12 minus b d cube by 12 divided by d by 2, which is y max. So you will get the equation for z as 1 by 6 into bd cube minus small bd cube divided by d. Similarly, in the case of a circular section, you can write the section modulus of the circular section as, if small d is the diameter of the circular section, we can write z is equal to pi d raised to 4 by 64 divided by d by 2, which is equal to pi d cube by 32. Now in the case of a hollow circular section, if capital D is the external diameter and small d is the internal diameter, we can write Ix is equal to pi by 64 into capital D raised to 4 minus pi by 64 into small d raised to 4. Now what is the distance of the extreme fiber from the neutral axis? Let this centroidal axis will be at a distance of capital D by 2. So you can write Zx is equal to, or Z is equal to I by y max, which is equal to pi by 32 into capital D raised to 4 minus small d raised to 4 divided by capital D. So this is how you can find out the value of section modulus for various sections. Now what is the section modulus for a rectangular section? Section modulus for a triangular section. For a triangular section, you can find out the section. Now you consider a triangular section. Let D be the breadth and H be the height of this section. So you can write I is equal to, Ix is bh cube by 36. Y max is equal to distance of neutral axis from the extreme fiber, 2 by 3 of h. So we can write Z is equal to I by y max, which is equal to bh cube by 36 divided by 2 by 3 of h, which is equal to bh square by 24. So this is the equation for section modulus for a triangular section. Okay, thank you.